Welcome to this explainer. Okay, let's dive right in. Today we're demystifying LV busbar arrangements. When you look at a single line diagram, it's super easy to just see lines on a page. But we are going to reframe those lines from mere drafting preferences into critical, high-stakes engineering choices, because really, they are the true electrical backbone of your facility.
We really have to start by imagining the ultimate nightmare scenario, a hospital or a massive data center going entirely dark. So, how much outage can your load tolerate? For a commercial office building, sure, maybe they can handle a few hours in the dark. But for continuous process plants or critical infrastructure, no way. The answer is literally zero.
So, here's our roadmap for today. We'll look at why busbar topology matters, single and sectionalized arrangements, double and transfer bus bars, the ring bus system, and finally fault duty and those crucial IEC standards.
All right, Section 1, why busbar topology actually matters.
When you really get down to it, it all comes down to an inevitable trade-off between initial cost and redundancy. A single bus bar, yeah, it's low cost, but it offers practically zero redundancy for anything beyond a small commercial space. But as you scale up to a double or ring bus bar, your redundancy and maintenance flexibility just shoot right up to high. The catch? Well, the cost goes right up with them. It's a constant balancing act against the load's criticality.
Which leads us right into Section 2, single and sectionalized arrangements.
So the single bus bar, it's compact, it's cheap, and look, it's the default for a reason. But its glaring weakness is that a single bus fault, or honestly, even just a planned maintenance event, is going to interrupt every single connected load. Because one common bus is serving everything, you have absolutely zero redundancy. If that bus powers down, the lights go out, period.
To solve that exact vulnerability without, a massive price hike, we step up to the sectionalized single bus bar. By just adding a bus section, you suddenly gain fault containment. An issue on one split doesn't just automatically force the healthy, independent section offline. This gives us what engineers call partial N-1 resilience. Basically, it means you can lose one section, but the rest of the system survives.
Now, the absolutely crucial point here is understanding the difference at the switching level. A section breaker divides a single continuous system, right? While a coupler links entirely distinct, independent bus systems together. It's a subtle distinction, but it dictates exactly how power gets routed during an emergency.
And as those emergency stakes get higher, we hit Section 3, double and transfer bus bars.
All right, here is the key distinction we need to make. A double bus bar gives you full continuous parallel redundancy. A transfer bus, on the other hand, is kind of like a cheaper alternative focused strictly on letting you do breaker maintenance without dropping the load. In a transfer setup, that second bus normally just sits there completely idle. It's a maintenance path, guys, not a true permanent supply.
Now, a double bus bar layout really shines when uptime is worth far, far more than the physical cubicle count. It gives operators just incredible flexibility to isolate one bus while the other keeps the whole facility running. Because you've got two separate main bus bars running in parallel, your outgoing feeders can actually be selected to run on either one. Honestly, it's the absolute gold standard for continuous service.
But if we want to go even further, we look at Section 4, the ring bus system.
So with a ring bus, if one section gets isolated, the remaining loop just acts as an alternative path. It feeds the connected circuits from the opposite direction. Every single source or feeder is hooked up through its own breaker position right in this loop. It provides incredible resilience. You can literally cut off a section for maintenance and the power just seamlessly flows the other way around the circle.
But of course, there's always an engineering trade-off, right? Operating an open ring safely limits your fault currents. A closed ring, however, maximizes your redundancy, but at a huge cost. Running closed means that if a fault happens, power from all those connected sources is going to rush toward that single fault point simultaneously, and that creates massive short-circuit challenges.
And dealing with those challenges is exactly what Section 5 is about, fault duty and IEC standards. This actually brings us to the villain of our story, the mechanical penalty you pay for all that reliability. That rushing power I just mentioned, it creates massive, really destructive forces. As you increase those parallel paths to prevent outages, you dramatically increase the short-circuit current the assembly has to survive. Look, a single bus bar, pretty low challenge. But a closed ring bus, that combines all those sources into a very high challenge level.
To tame those massive fault currents, engineers rely on some very strict IEC frameworks to verify that the theoretical diagram can actually survive brutal reality.
IEC 6099 is what calculates just how massive that fault current will be. Then IEC 6143 and 6080-65-1 step in to make sure the physical copper conductors won't literally bend, melt, or just rip apart from the sheer electrodynamic stress. It's intense stuff.
So the ultimate takeaway here is this. Reliability and withstand are permanently linked. The exact topologies chosen to keep your critical power flowing are the very same ones that demand the most rigorous thermal, mechanical, and electrodynamic verification. The safest layout is very often the hardest one to engineer. You simply cannot design for high availability without also designing for extreme fault survival.
When you're comparing initial capital against life cycle costs, you really have to ask yourself, is the upfront savings on a simple radio layout actually worth the devastating cost of an unplanned facility shutdown tomorrow? Answering that correctly is what separates standard design from truly resilient architecture. Keep that multi-million-dollar question in your back pocket the next time you're choosing a busbar arrangement. Thanks for tuning in to this explainer.